Hey everyone, this is John Buck, and I'm back with another discrete time linear systems video. In this video, I'm going to talk about a technique called partial fractions. That's an idea to take apart a product into a sum of first order terms, and that turns out to be very important to let us find inverse Fourier transforms simply for complicated functions that will come up often when we're looking at the output of linear systems, and we'll also see it very soon in a video we'll exploit this technique to find the impulse response for very complicated difference equations without having to turn the crank and guess a pattern. The nice payoff for this technique is it'll let us be able to go through a process mathematically and be guaranteed to figure out what the impulse response h of n is. So for today's video, I'm just going to highlight the technique itself. We'll see in future videos how we use it to find different, like I said, finding outputs or finding impulse responses. But the basic idea is that if I want to find the inverse Fourier transform of something that looks like this, where it's a ratio, it's a fraction like this, and the numerator and denominator are both in terms of things like e to the minus j omega. And these are the ones that will come up a lot in discrete time linear systems because, as we've seen, multiplying by this complex exponential represents something being delayed somewhere. And so if we first look at this, we say this is kind of intimidating because we haven't seen one with more than just e to the minus j omega. Seeing one with higher omegas in it isn't something we've seen yet. But the first step in getting going with this one is to recognize that we can actually factor that denominator into a product of things we've seen before, or I'm sorry, product of first order terms. So we're not going to worry about the numerator yet, but we'll start with the denominator and say, well, I can factor this into 1 and an into a product of two things that when I FOILed them out, it would give me that. And then I just need to figure out, well, what, right? I have a 1 at the front, and then I'm going to have an e to the minus j2 omega from these two, and then I'll have a cross term when I put them together. And I need to either use a quadratic formula or practice it. I would usually look at this and say, well, let's hope it's something that's direct. In real life, it may or may not be, but here I need two simple fractions that multiply to give me minus a sixth. So it's either plus a half and minus a third, or minus a third and plus a third, or it could be like 1 and a sixth. But I'm going to go with looking at this middle term. I say, oh, I need the combined thing here to be a sixth too. And so after a little trial and error of practice, I might look at this and say, well, if I have, actually I need plus a half and minus a third. When I FOIL this out, right, I'll have a 1 for the first term. I'll have minus a sixth e to the minus j2 omega for the last one. And then in the middle term, I'd have minus a third e to the minus j omega and plus a half. And so a half is 3/6, a third minus a third is minus 2/6, would leave me the right thing here. So if you're agile at factoring them like this, it helps. Otherwise, you can solve these using the quadratic equation or a calculator to figure out what the roots are and do it like this. But we do want to have it in this form because these are things now I say, well, if I just had one of those terms in the denominator, right, I just saw one that looked a lot like this, and it would be something to do with 1/3 to the n u of n. And I could work out this one using the same exponential form if I only had one of them. But I don't know what to do with both. And the trick is to say, well, what if this was the reason I got this? The way to look at this is say, what if I got this because it was a least common denominator? I'd multiplied together a sum. And that's sort of where we call it the partial fractions, is we say there's some way to take this apart so that it's a sum of two fractions. And why I like the sum better is, well, the Fourier transform is linear. I can take the inverse transform of one at a time, get two different time signals now, that these are just what we call first order terms. There's just a single e to the minus j omega. The question is, I have unknown constants up here. So I'm sort of saying if I put these back together, if I had been going in this direction, I have a times this. The numerator would be a times that denominator plus b times that denominator. I need to pick a and b to get this 9 minus e to the j 2 omega here. Clean up that extra parenthesis, it didn't need to be there. And so how am I going to do this? Well, I'm going to end up with a system of two equations. I'm going to recognize that if I put these back together, and then match them, I could get them back. So I'm gonna do this using a little bit of color to set up how I'm going to solve the equations for a and b in a second. So when I multiply these together, I'm going to keep the constant terms in green, or maybe I'll leave the constants in white. So I have a, and then I'll do the other ones in red. So I'll have plus 1/2 a e to the minus j omega, right? That would be this term here into the numerator. And then when I multiply the second numerator by the first denominator, I'll have b, and I'll have minus 1/3 b e to the minus j omega, all over, right, the common denominator would be 1 minus 1/3 e to the minus j omega, and 1 plus 1/2 e to the minus j omega. And how I'm going to find a and b is I'm going to set that equal to my original numerator. I was like, well, I actually know what I want these a and b's to give me. So I can say I know this is equal to, like, the same denominator. I'm not going to write it to save time, right? I have the same thing here. Well, I could actually be trying to be clever. And use a copy-paste on the denominator. So I say I have the same denominator. So I've got my copied denominator over there. Moved it a little further than I meant to, but. And then the numerator, again, using the same color coding, when I bring it down, I'm going to bring this numerator down, say that's what I want. And I'm going to code, I've got a 9 for the constant, and I've got plus 2e to the minus j omega for the other term. And the reason I've coded it this way is if these things are going to be equal all the time for every omega, I have two equations that come out of this. One is in the white and one is in the red, that the constant terms have to be satisfied everywhere, and the red term, the e to the minus j omega terms have to be satisfied everywhere. So if I pull those out, it gives me two equations and two unknowns. So I have, the first one, we'll do it one more time in color just so people see where it comes from. I have a plus b is equal to 9. And then I also have 1/2 a e to the minus j omega, which is this term, minus 1/3 b e to the minus j omega is equal to 2 e to the minus j omega. Right? So I've got this term plus this term equals that term. And looking at these, I can multiply through by, or divide through by e to the minus j omega, right? That cancels out everywhere. And so the red equation is my second equation, where I have 1/2 a minus 1/3 b equals 2. Sort of looking ahead, I'm going to want to multiply that to get rid of the fractions. I'll multiply by both sides of this equation by 6 to get 3a minus 6 times a third is 2, so minus 2b equals 12. Right, so this is now, I have two equations and two unknowns. A plus b equals 9, 3a minus 2b equals 12. So to solve this, I'm going to turn this one around. So I'm going to have b is equal to, I can turn this into b is equal to 9 minus a. So I can plug that in now down here for b. And so when I do that, I'm going to go back to just using my normal white color here. So 3a minus 2 times 9 minus a equals 12. And so doing a little algebra to clean that up, I'll have 3a minus 18 plus 2a equals 12. Move the 18 to the other side and combine the a's. I have 5a equal 30. So a equals 6. And then b, we have above, is 9 minus a up here. So that's 3. So how does that help us? Well, coming back to where we started, I've now got this equation here. So a is 6. sure I get it right. It's very easy to do all this work and then put the wrong one in the wrong place. So a is 6 over 1 minus 1/3. So when this is all done, I've got x of e to the j omega is equal to 6 over 1 minus 1/3 e to the minus j omega plus 3 times 1 plus 1/2 e to the minus j omega. I've been doing these for dog's ears, and I still double check because it's easy to get them backwards. So it's kind of easy once you have this to look and say 6 times 1 plus 3 times 1 is 9, which is the right constant, and then 6 times 1/2 is 3, minus 3 times 1/3 is minus 1, so I have 3 minus 1 is 2, and that matches what I started out with. Right, so that gives me the right numerator that I was starting for. So I've used this algebra trick to break this into 2 terms, and that's a lot of algebra and 2 equations and 2 unknowns, and we'll see some examples later might even have 3 equations and 3 unknowns. But the payoff is now these are trivial inverse transforms. Right, we say, well, I've already seen 1 over 1 minus 1/3, this first term here. Right, this denominator is like would give me a third to the n u of n. So if I put that in here, I can say, well, x of n is just 6 times that. I've got 6 times, because of the 6 in the numerator, 1/3 to the n u of n. Right? If the numerator were just 1, I wouldn't need the 6 here, but scaling by 6 in frequency, I scale by 6 in time. Similarly here, I'll have 3 times, well, this is plus 1/2, which is like minus of minus 1/2 e to the minus j omega. So this means my a, I have a to the n u of n, but my a is now minus 1/2. Right, so doing that bit of extra algebra legwork made the inverse Fourier transform basically by inspection, because it turned it into common exponential ones we've seen before. So that's the idea with partial fractions, that we'll often see either coming from passing inputs through systems, we'll get output Fourier transforms. So maybe in future examples we'll see y of e to the j omega that looks something like this. Or we'll see soon using difference equations to find h of e to the j omega, we'll get impulse responses that look like this with combinations of terms. And then this idea of we break a large complicated ratio of things with higher order terms than e to the minus j omega into a sum of first order terms that we could then easily inverse transform is the payoff on what we call partial fractions. All right, so that's all for this time. Good algebra trick we're going to be using over and over again to make inverse Fourier transforms easier. So I wanted to break it out into its own video. See you next time.